Hi everyone, this is going to be the first lesson on the topic of electricity for GCSE physics students. In this lesson we're going to make a start looking at the idea of static electricity and electric fields. So let's quickly take a look at the learning outcomes for this lesson, and if ever you need to find what the learning outcomes are for a particular lesson, you can either go to the lessons page by going into the course navigation and clicking on the link for that lesson under the appropriate section, or you can go to the learning outcomes checklist here and click on the title of the lesson there, and you'll find the learning outcomes. So by the time you finish this teaching video, and if you're watching this on my website, by the time you complete all of the interactive questions that will pop up throughout this teaching video, and also the end of lesson quiz and various other learning activities associated with this lesson, you should be able to do the following. Firstly, we're going to look at the property of charge, because this is a fundamental characteristic of matter which allows us to understand what we mean when we use the word electricity or electric current. We then need to go on to look at some of the effects of static electricity, some of the more common effects that perhaps you will have noticed in everyday life, and perhaps some of the ones that you'll probably only see in a science laboratory. We then need to go on to look at the concept of an electric field. Now, we may not tackle these in this particular order, but ultimately by the end of this lesson and also the other learning activities other than just this teaching video, we should have covered all of these. And as always, if you have any questions, either while you're watching the video or after having watched it, then you can get in touch with me via the private messaging function. If you're enrolled on this GCSE physics course, you can find that on each page for each lesson. So if you have any questions about this lesson, you can go to this lesson page and send me a private message, and I will respond to your question within 24 hours. Alternatively, you can type your question in the live chat on that lesson and start a discussion with other students in which I'll also respond. If you're watching this video elsewhere, such as on YouTube, then go ahead and type any questions in the comments and I'll do my best to get back to you there as quickly as I can as well. So, before we get started then, let's take a look at some of the history of what we call static electricity. So it's thought that the phenomenon of electricity was probably first discovered by the ancient Greeks around 600 BC. There are other ideas. For example, you might want to look up something called the Baghdad battery, which arguably could have been an electrical device that was used much earlier than this in Mesopotamia. But at least in most Western accounts, the discovery of electricity was probably first made by the ancient Greeks around 600 BC. Now, they discovered that taking specific materials and rubbing them together could produce an attractive force between those objects made of those materials. So an example would be a fossil resin called amber, which could be made to attract relatively light objects such as strands of hair towards itself if it was rubbed with a cloth, for example. Now, in some experiments it was found that rubbing a piece of amber could also make it produce a spark. Now, it was probably Benjamin Franklin who was the first to carry out formal scientific investigations, at least in the Western world, on electricity. And in about 1752, it's said that he flew a kite in a thunderstorm, obviously not a particularly safe thing to do, and he attached a metal key to this kite. Now, based on these experiments and the fact that he got lightning to strike the key on the kite and then flow down the wire attaching the kite to the ground, he put forward the idea that lightning was a form of electricity, that there was somehow a connection between the phenomenon of lightning and the phenomenon of electricity. So his observations later enabled scientists to establish modern theories about the way that electricity works and what electricity is. So, in order to understand electricity, we first have to understand a few things about the structure of atoms. Now, this is probably something that we're going to go into in the third topic of this GCSE physics course when we start to look at atomic structure in a bit more detail. But for now, we do need to understand a little bit about atoms in order to understand what we mean by static electricity. So, looking at the structure of an atom is the smallest particle that composes a chemical element. And so atoms are typically modeled using diagrams like this one. And you have a small central nucleus containing most of the mass of an atom, and the nucleus is made up of particles called neutrons and protons. The electrons are tiny particles which orbit the nucleus in these specific energy levels at specific distances from the nucleus. So all matter is made up of atoms. Atoms are composed of protons, neutrons, and electrons, and the nucleus is the portion of the atom in the center where you find the protons and the neutrons. Now, these particles all have a specific known quantity of mass. Mass measures the amount of stuff, physical stuff, that an object is made of. But they also have, typically the protons and the electrons, they have a charge as well. So charge, like mass, is a fundamental property of matter. It is a scalar quantity as opposed to a vector quantity, meaning that it simply has a certain size or magnitude, but no specified direction. So protons carry a positive electrical charge, neutrons don't carry any charge, they're said to be electrically neutral, and electrons carry a negative charge. Now, atoms, when they are in the when they are atoms and not ions, atoms have overall no electrical charge, and the reason for this is that any atom of any element always has exactly as many protons as it has electrons, and each proton has exactly the same amount of charge as an electron. The protons have a positive charge, the electrons have a negative charge, but they carry the same amount of charge. And so if you have an equal number of protons versus an equal number of electrons, overall the total charge adds up to zero charge. There is no overall charge on an atom. So for this reason, atoms are electrically neutral. However, if an atom loses electrons, then it will end up with a situation where it has more protons than electrons, more positive charges than negative charges, and therefore the overall charge of the atom will no longer be zero. It will carry an overall positive charge. At that point, we don't call it an atom anymore, we refer to it as a positively charged ion, or a cation. Now, if an atom gains an electron, it will have more electrons, more negative charges, than it has protons or positive charges. And so since the negative charges outweigh the positive charges, the overall charge on the atom will not be neutral anymore, it will be negative. And so at that point we no longer have an atom, we have a negatively charged ion, or an anion. Now at this point we need to mention a few things about charge. Charge is a fundamental property of matter. And as we see, since matter is made up of atoms, and atoms are made of these positive, negative, and neutral subatomic particles, protons, electrons, and neutrons respectively, then since all matter is made up of atoms, then all matter contains charged particles. So before we go any further then, let's define what we mean by charge a little bit more formally and connect it to some other ideas a little bit later on. So in physics, we need to be aware of the standard units of specific types of quantities, like charge, like mass, and so on. Standard units of mass, for example, are kilograms. Standard units of charge, which usually is given the symbol Q when we put it into equations, standard units of charge are coulombs. Now this is named after a very famous scientist whose surname was Coulomb. We'll be encountering that in an A-level physics course when we talk about Coulomb's law. But charge is measured in units called coulombs. So the units of charge are coulombs, spelt like this. Now the letter that we use to abbreviate this unit is the capital letter C. So charge is simply a quality of materials. An atom has no overall charge as long as it has an equal number of protons and electrons. Now, protons are said to carry one positive atomic unit of charge. So protons, in terms of their charge in atomic charge units, which are not standard units, they're not coulombs, protons have one positive unit of charge, 1 plus. Electrons have one negative unit of charge, and neutrons, being electrically neutral, have zero charge. They have neither positive nor negative, and they have no units of charge on them. But these are atomic charge units. Now, the reason why we use these units instead of standard units of charge when we're referring to the amount of charge on something like a proton or an electron is because these are incredibly tiny particles, and to express the amount of charge on a proton or an electron in standard units of coulombs, we could do that. So if we express it in coulombs here, it would be what we call the elementary charge. These are called elementary particles, and so the charge on an elementary particle is a specific number in coulombs, and it's actually the smallest charge that can exist on a particle that can be isolated, like a proton or an electron. And so you can't have a smaller unit of charge than the elementary charge, because you can't have a particle smaller than a proton or an electron that can be isolated by itself. Now, I know some of you are joining me here live, the students in attendance with me. You've asked me to discuss things which are a little bit more advanced, things like quarks and things like that. Quarks, yes, are smaller than protons and electrons. Yes, they are particles, but quarks cannot exist in isolation. They don't exist in isolation. They exist in relationships to each other. And so you can have a smaller unit of charge on a quark. A quark can carry 1/3 of this amount of charge, but a quark is not a particle that can be isolated on its own. And so the elementary charge is still the smallest unit of charge that can exist in ordinary particles like protons and electrons that can be isolated. Now, I'm going to be going over some of the other questions that you guys have asked me towards the end of this lesson, as always, in the Q&A section, which will follow the recorded segment of this lesson. But for now, just remember that the standard unit of charge is coulombs. Now, we measure the atomic units of charge in a different unit. We use atomic units of charge. We assign 1 to the charge on a proton. Now, this amounts to the elementary charge, and the elementary charge is 1.67 times 10 to the power minus 19 of a coulomb. It's an incredibly small fraction of a coulomb. Now, we measure the actual charge, the atomic unit of charge. 1 atomic unit of charge is equal to the elementary charge. Now, the elementary charge is 1.6 times 10 to the power minus 19 of a coulomb. It's an incredibly small fraction of 1 coulomb of charge. Obviously, you're dealing with very tiny particles, and therefore the amount of charge that they carry will be a tiny fraction of the full 1 coulomb of charge, one single unit of standard unit of charge. So a proton carries positive 1.6 times 10 to the power minus 19 coulomb of charge. An electron carries minus 1.6 times 10 to the power minus 19 coulomb of charge. So this here is the elementary charge, the smallest unit of charge that can exist on an elementary particle. Neutrons carry no charge. Now, these are horrible numbers to work with, and so scientists, when they're describing the amount of charge on a proton or an electron, they use the symbol 1. They use the number 1 in atomic charge units to stand for this number. And so this is the amount of charge on a proton or an electron in standard units, but to make life easy for ourselves, we simply say that this amount of charge is 1 unit. So a proton has 1 positive unit of charge, an electron has 1 negative unit of charge. So this is what charge is. It is a fundamental property of matter. It can be positive, it can be negative, and it is carried by particles such as protons and electrons. So if an electric current now, as opposed to a static charge, is a moving charge. It is the flow of electric charge, and in electrical circuits it's carried by electrons. Now, going back to our definition of charge here, charge is given the symbol Q, and it's measured in coulombs. Now, you've probably come across electric current in previous years of your science education. Electric current, is given the symbol I in equations, and the units of current are amperes, again named after a very famous scientist, which we'll encounter later. Amperes, or just capital A for short. Now, this brings us to the first of our equations. A current is when there is the net flow, the average movement of charge. So this word here, current, is defined as the net or average flow of charge in one direction. So notice that the definition here is the average flow of charge. It doesn't necessarily have to be negative charge like that carried by electrons in electrical circuits. It can also be the average flow of positive charge in a particular direction. But in electrical circuits where the majority of the components are metals, it is in fact the electrons that move around the circuit. And if they all move in one average direction, average net direction, then you have an electric current. So to measure an electric current, we have to measure a flow of charge that is happening with respect to time. So here is the relationship between current and charge. So current, I, is equal to the amount of charge that flows past a fixed specified point in every second. So we can write the following equation. Current I is equal to the charge Q over the time T. So this literally translates as charge per second. So again, current is in amperes, charge is in coulombs. So these are the units of these quantities here. And time, the standard units of time in physics are seconds. So 1 ampere of current is equivalent to saying 1 coulomb of charge flowing past a fixed point per second, coulombs per second. So we've defined what we mean by an electric current. So in certain circumstances, there can be a buildup of electric charge which is not free to move and flow in an electric current. This is called static electricity. Now the word electricity is a little bit of a kind of vague word really. When people say electricity, particularly if they're not scientists and they're not using it in a scientifically rigorous sense, it's not really a very useful word. It doesn't really mean much. It doesn't allow us to distinguish between phenomena like static electricity or current electricity. But if an electrical charge builds up on an object and that electrical charge isn't going anywhere, then you have a static charge, static electricity building up on an object. So if you have an excess of electrons, if you have lots of electrons building up on an object, then you have an excess of negative charge, and so you have a negative static charge. But if you take away electrons from an object, then you have more protons than you have electrons, and therefore you're going to have an excess of positive charge. So you'll have a positive static charge on that object. Now, if static electricity continues to build up in one place, it can result eventually in a spark, or if somebody's touching that object, in an electric shock. Now this occurs because the electrons will move from one object to another to equalize that charge. Now protons obviously play an important role in this science of electrostatics, the study of static charge on objects, because they provide the positive charge within atoms. However, the protons are tightly bound inside the nuclei of atoms and are not able to move under ordinary circumstances. It's the electrons which are the particles able to move, and these are the ones which are responsible for electric sparks, discharges, and electric currents through things like metals. So, speaking of metals, let's take a look at what actually happens when an electric current flows through, for example, a wire or an electrical device. Now, metals they have a certain structure. Those of you who go on to study GCSE chemistry, you will eventually look at something called metallic bonding, which is the way in which the particles within a metal are stuck, bonded together. And the way that it works basically is that each metal atom in the metal has become a positively charged metal ion by giving up its outer electrons and sharing them with all of the other metal ions in that piece of metal. The electrons are free to move between the metal ions like this, and they move randomly. Now, if we're looking at this situation, let's imagine that this end of this conductor here, let me just highlight my cursor again. So if we imagine that this end of this electrical conductor, if it's, for example, a piece of metal or a wire, This is one end of it, and this is the other end. You can see here that on average, because the electrons are the delocalized free electrons which are moving around, because they're moving at random, at any given moment you have roughly the same number moving in one direction as you do in the opposite direction, and therefore you have no overall electric current. Remember, a current is when you have a net or average flow of charge in one specified direction. At the moment, there are just as many electrons moving in one direction as there are in any other direction, and so there is no net flow of charge. However, if a current is flowing through this wire, you have a different situation. You have electrons moving on average from one end of the conductor to the other end in one average direction. So this is the distinction between when a current is flowing through a metal and when a current is not flowing through a metal. So in electrical circuits, which again are made up of wires and devices which predominantly feature metallic parts, the electrical current which is flowing in the circuit is simply the flow of electrons. And when we're measuring the current, we are measuring the amount of charge carried by those electrons which is flowing past a fixed point in every second. So the flow of electrons is what we call the current. Now the size of the current depends on a number of factors. It depends on how many electrons are passing this fixed point per second, and that in turn will depend on the amount of work the power supply is doing in pushing those electrons around the circuit. Now we'll get to the concept of voltage in the next lesson. We're going to be talking about the reason why electrons move around, and we're also going to touch upon it in this lesson when we get to the subject of electric fields a little bit later on. So we have two general kinds of materials. We have electrical insulators, which typically do not allow electric currents to flow through them, and we have electrical conductors, like metals that we saw in the previous slide, which have delocalized electrons which are free to move through those metals. So in an insulator, such as for example a plastic, electric charge can't flow because the electrons in the atoms that make up the plastic are tightly held on to the atoms and within the bonds, the chemical bonds between those atoms. Those electrons can't flow freely through that material. So insulating materials such as plastics are obviously very useful in certain circumstances. You may want to use them as electrical insulation around the conductor, copper in this case, within a wire. But in some situations, insulators can develop a static charge. So let's look at how we build up a static charge. So if we take two insulators, such as for example a piece of wool and a piece of polythene, both of these are electrical insulators because the electrons are not free to move within these materials. But if we then rub these together, what can happen is the electrons from one piece of material, from one insulator, because of the friction between the two surfaces, can be stripped off and move over to the other piece of material, the other insulator. But remember, all atoms start off electrically neutral. So before we started, the atoms in the wool had exactly as many electrons as they had protons, and so the positive and the negative charges cancelled each other out, so you have an electrically neutral piece of material here. The same thing for the polythene, but when you rub them together, friction will cause some of the electrons from one material to be transferred to the other material. So now the wool becomes electrically positive overall because it has more protons than it has electrons, and the polythene, in contrast, becomes electrically negative overall because it has more negative charges. The electrons outweigh the positive charges on the protons. So now we have a positive static charge on this object and a negative static charge on this object. Now this can cause objects which have been charged by friction like this to stick together. And you may have seen this if you take, for example, a balloon and rub it against somebody's hair like this. Again, we have the transfer of electrons from the hair to the balloon, and so now the electrons have become stuck to the surface of the balloon so that the balloon has more electrons than protons and the hair has fewer electrons than protons. So the hair has an overall positive charge, the balloon has a overall negative charge. So we've just explained how this causes the balloon to become negatively charged. Now, you may have also seen that balloons that have been lying around, perhaps on fabric surfaces, if you then pick them up and put them against the wall, sometimes they will stick to the wall. This is due to charging by induction that we'll talk about a little bit later on. So another device that you may have come across in the science laboratory or elsewhere is the Van der Graaff generator, and this can be used to create a static buildup of charge on objects. So here's how it works. So you start the Van der Graaff generator, you'll see this rubber belt start to move through the Van der Graaff generator, and we'll see in a moment how this negative buildup of charge occurs and builds up on the dome, and eventually this will cause a spark when there are so many electrons on here that they will jump across this gap to this device over here, which is connected to the ground via an earth cable. So there are many types of Van der Graaff generator, and they work in many different ways. Now the model that we're looking at works in the following way. So as the belt turns, the electrons are picked up from the comb. The right side of the belt, which is rising here, that you saw rising in that animation, becomes negatively charged, and then it carries the electrons upwards. Now the reason for this is because as it moves in this direction, as we'll see, there is an excess of negative charge on the belt here. So inside the dome you have a brush here. So you have something called a comb down here, and you have a brush up here. So the comb is attached to another material, and as the rubber belt brushes against the comb, it strips electrons from that material so that it's carrying an excess of electrons. And then when it comes up to the brush at the top here, this brush is connected via a metal connection to the inside of this metal dome. And so these electrons will flow through that metal, because again the metal is a conductor, and will build up on the outer surface of this dome. The dome, obviously, because it's building up electrons, will eventually become more and more negatively charged. Now again, in contrast, the side of the belt that's coming downwards here is electron deficient. It's positively charged because it's given up a lot of electrons to the brush here and to the dome. Now as the positively charged side of the belt comes down to the bottom roller, it will again regain electrons from the comb and then will carry them back up, and so the process continues, building up more and more negative charge on the surface of the dome. Eventually, once a high enough electrical charge and negative charge is built up on the dome, that charge will discharge itself across the earth, the gap to the earth dome nearby, and you will see this as a spark. The spark is actually made visible because as the electrons jump across this gap, they will ionize the air molecules, and those molecules will give off a certain amount of light. And so the electrons jump across this gap and then flow down here into the ground via this earth cable. So we can use a Van der Graaff generator to do various demonstrations involving the charging of objects. So we can place a metal tray here with some aluminium spheres in the metal tray. So all of these objects are metal, they're connected to the dome, and what will happen is you will see eventually these little metal spheres start popping out of this tray here. So the explanation for this is that as the negative charge builds up in the dome, the electrons freely pass to the aluminium spheres because both the cup and the spheres themselves are good conductors, they are metals. So as a result, the aluminium spheres also build up a negative charge, but because the spheres are sitting next to each other, touching each other, the negative charges start to repel each other. As we'll see when we look at electric fields, like charges will cause forces of repulsion between each other that will push those apart. So essentially, as the negative charge builds up, the aluminium spheres start to push apart from each other, and eventually the charge becomes big enough so that the repulsion becomes great enough to cause these negatively charged aluminium spheres to pop straight out of the tray that they're in. Another interesting demonstration using a Van der Graaff generator is being able to light a Bunsen burner using nothing but the tip of your finger. So what you'll do is you will have the Van der Graaff generator turned off. You will put one hand on the surface of the Van der Graaff generator, and then with your other hand you will bring it closer and closer to the Bunsen burner until you will see a spark jump across the gap. Now, if the gas is flowing out of the Bunsen burner, the heat from the spark will actually ignite the Bunsen burner. So the Van de Graaff generator can produce a voltage high enough to allow a spark to jump from the tip of your finger to the Bunsen burner. So the reason why this happens is because the surface of your body is picking up an excess of electrons from the surface of the Van de Graaff generator, as long as you are wearing shoes or footwear that insulate you from the ground. And so your body is building up a static charge on its surface. Now, because your fingertip gets close to the edge of the Bunsen burner, the static charge that's built up on the surface of your body can jump across that gap to the Bunsen burner. And so for this reason, a lot of steps are taken to reduce the buildup of static charge whenever there are situations in engineering, for example, where there are flammable fuels involved. So in the refueling of aeroplanes, for example, as we'll see a bit later on, there are a lot of precautions made by engineers to prevent the buildup of static charge, because one spark could ignite the gases from the fuel in the aeroplane's tanks, and this could obviously cause an explosion. So this is a demonstration here of the fact that positive and negative charged objects can exert forces on each other. Now this will bring us eventually to the idea of electric fields a bit later on, but for now this is something that you probably will have seen in earlier years of your education in science. If you haven't seen it yet, most likely you will see it in one of the demonstrations or practicals that you'll do in the science classroom. So what we have here are a couple of acetate or plastic rods, one of which has been charged and the other one has been charged as well, one of which is hanging by this cradle here from a string, so it's free to rotate. So if we imagine that the rod in the cradle is positive and the rod in the hand is negative, we can see, or both positive rather, let's see what happens here. We'll see that under these circumstances where both of these objects are positively charged, they will repel each other. The one in the cradle will rotate so that it's pointing, so it's moving away from this one. If we change this situation to the rod in the hand being negative, you'll get it moving towards it. So we can see here that a positive object will attract a negative object and vice versa, but two positive objects will repel each other. Now, if we take two negative objects, they will also repel each other. So this tells us something about charges. Not only can they exist in positive and negative, but objects which have a positive charge will attract objects which have a negative charge and vice versa. Positively charged objects versus positively charged objects will repel each other, and negatively charged objects versus negatively charged objects will also repel each other. So we can summarize this by saying that like charges, meaning positive, or rather opposite charges, meaning positive and negative, will attract, and like charges, positive versus positive, and also negative versus negative, will repel each other. Now the reason for this is because of the idea that there is a field around a charged object, and we'll get to the concept of the field a little bit later on. It's a very important concept. But before we do, let's take a look at some basic ideas. So we'll talk about the basics behind this. So why do electrostatic forces attract or repel each other? So here we can see somebody's hair being attracted to the surface of this rather old television here. So a charged object creates an electrostatic field around it. So this field will affect the space around the charge in a similar way that gravity affects the space around an object such as the Earth, or a magnet affects the space around a bar around itself. When a charged object enters that electrostatic field, that object will experience a force, and that force can either be attractive or repulsive. Now I'll demonstrate this in a bit more detail a little bit later on, but for now let's take a look at some kind of everyday demonstrations of this principle. So when a charged object moves near to an uncharged object, a charge can be induced or caused on the uncharged object due to the electrostatic field around the charged object. So this is called electrostatic induction. So the example that I mentioned earlier is you take a charged balloon. So for example, this is a balloon that's been rubbed against the couch cushions or against your hair. It's got an overall negative charge because it's taken electrons due to the friction of that rubbing from those other objects, and it has more electrons on its surface than it has protons. So the overall charge is negative. If we then move this towards a wall, the wall started on this surface having the same number of positive and negative charges, but because the negatively charged object comes close to the surface of the wall, the negative charges here will repel the electrons, will push the electrons away from this nearer surface of the wall over to here. This will cause this nearby surface of the wall to have an overall positive charge. This is called an induced positive charge because it has been caused or induced by the nearness of this negative charge around the balloon. And so, again, opposites attract. You have a positive charge on this surface of the wall, the induced positive charge. You have the negative charge on the surface of the balloon. They will attract each other and the balloon will stick to the wall. So after the charge has been induced on the wall, these surfaces will attract each other and the balloon will stick to the wall. So we can explain many phenomena by means of the principles of electrostatics. So, for example, why when you comb or brush long hair, it can cause the hair to stand on end. So this rather perplexed looking dog, for example, has had its hair brushed, and as you can see, some of its hair is standing up. And this is as a result of the hair building up a static charge. We can also explain why an electrostatic charge can jump from you to another person or object. If the charge is large enough, it can cause a spark as it leaves your body. So again, a common example is when you touch a conductor such as a metal door handle after walking on a nylon carpet. Other effects, so for example, why do monitors and televisions often get covered with dust and need frequent wiping? Again, this is due to electrostatic charge building up on the surface of the screen and attracting dust particles in the atmosphere towards the screen. We can also explain what we saw before, the television screens, particularly these old cathode ray tube monitors and televisions attracting hair. We can also explain lightning in a similar fashion. Lightning is an electrostatic effect which is caused by clouds developing a charge as they move past each other. The negative charge in the lower portion of a thundercloud induces a positive charge on tall trees and the tops of buildings. Now the potential difference, the voltage created between those 2 points, causes an electrostatic discharge down to the earth, which we see as a lightning bolt. So, let's have a look at combing hair with a plastic comb and explain how this works. So we take a plastic comb, and again, the plastic is an insulator. If you do this with a metal comb, it won't work in quite the same way. We can then use that charged comb to pick up small pieces of paper from a surface. So you're combing your hair with the plastic comb. The plastic comb is typically made from a polymer such as polythene or polyethylene. The comb pulls some of the electrons from your hair and becomes negatively charged overall as a result. If you then hold this charged comb over some pieces of paper, a positive charge is caused or induced on the pieces of paper near the comb. They then are attracted by the comb, and the attraction is enough to overcome the weight of these pieces of paper and pull them up onto the comb. So I mentioned that this would not work with a metal comb. Metal is a conductor, so any static buildup, any buildup of electrons on the surface of a metal comb is immediately shared equally through the body of the comb. So the metal comb would also easily pass its charge on to the person that was holding it, and the person holding it would be acting as an earth for that charge. So for these two reasons, metal objects can't be charged by friction, although they can be charged by induction. Now, many of the more advanced examples that appear in for example, in the lesson quiz, the interactive quiz for this lesson, will require you to explain charging by friction, induction of charge, and also the charging by induction of metal objects. But again, I'm not going to go into those here because otherwise this lesson would be way too long. This lesson is going to be long enough as it is. I realise, again, those of you joining me live on Zoom, some of you have asked those questions. I'll happily go over those with you in the recorded segment of this lesson. But like I say, if you have any questions at any point, you can always get in touch with me. I'll happily answer those for you. And also the interactive quizzes do contain full explanations for all the questions. So if you do the quiz, always check the quiz review or explanations or answers button at the end so that you can go back through the questions that you answered and see the full explanations for them. So, attracting hair with a charged comb. So if we rub a comb through somebody's hair and it's the cone is made of an insulating material, it will pick up electrons from that person's hair. And we can then take that charged comb over to somebody else's hair and we'll see that it will actually attract that person's hair towards itself. Now the explanation for this is, again, it's because the comb takes on an overall negative charge because it has been charged by friction. It has stripped off electrons from the first person's hair, and so it has more electrons than protons and has a static negative charge on it. This will produce an electrostatic field that attracts or will induce a positive charge on the other person's hair, and the positively charged ends of that person's hair will then be attracted to the negative comb. Now, another really interesting phenomenon that you can see, that you probably will either have seen already or your teacher will demonstrate for you, is if you take a charged object, such as, for example, our charged comb, and put it near a thin stream of water coming from a tap, you'll see that the stream of water will actually bend towards the charged comb. Now, the reason for this is that water is made up of molecules which are polar. They have a slightly positive end and a slightly negative end. And so the negatively charged comb induces positive charge on this end of the stream of water molecules. As the water molecules are free to move, the water is then attracted to the comb along this side. So what about getting a shock from a carpet? Well, if you walk over a nylon carpet, your body will take up an overall negative charge because, again, the friction between the soles of your feet and the carpet will have stripped electrons from the carpet, which will then build up on the surface of your body. As you then move your fingertip towards the door handle, this can then cause the electrostatic charge that's built up, those electrons on the surface of your body, to jump across this gap. And this is what you will experience as an electric shock. So, to fully explain this, we can say that when you walk over a nylon carpet, your shoes pick up electrons from the carpet. The electrons spread over the surface of your body, which takes on an overall negative charge. When you approach the door handle, the negative charge on your fingers induces a positive charge on the door. It causes, again, the door handle is made of metal, and so the electrons on the surface of the door handle nearest your fingertip will be pushed away by the negative charge on your fingertip, leaving a positive charge on that part of the door handle. And so, as your finger approaches closer, eventually a transfer of electrons will take place between the tip of your finger and that region of positive charge on the end of the door handle, and this is what causes the spark, which you experience as an electric shock. Now, the dust on the TV monitors. So this again is due to electrostatic charge buildup. Now, again, some electrical monitors and TVs are worse for this than others, but essentially due to the way these devices function, they gain a static electric charge on their surface. Now this induces an opposite charge on dust particles, which are very lightweight, uncharged particles, but when they come close to the TV monitor, the negative charge on the monitor induces a positive charge on the nearby dust particle. This then causes them to attract each other, and therefore the dust is attracted to the surface of the screen and builds up over a long period of time. Now, the phenomenon of static electricity obviously does cause certain hazards, but also allows us to use the phenomenon of static electricity for various applications as well. So let's take a look at those. In the United Kingdom, on average, about 3 people a year are killed by lightning. And so, typically, buildings and large structures will have lightning conductors, lightning rods on them. But so, for example, on the evening of the 17th of November of 2006, there was a teenage boy who died on his way home when he was hit by a bolt of lightning because he had made the unfortunate mistake of sheltering under a tree during a severe thunderstorm. And in 2001, forest fires threatened to destroy houses in the suburbs of Sydney in Australia, and this fire had been started by lightning. In 2006, in July, there was a thunderstorm that hit an area of Washington in the US. One house was struck by lightning, and this caused the television in that house to explode, and this in turn caused the house to catch fire. So you can see here, obviously, that there are many hazards associated with these phenomena. Now let's take a look at lightning then. So lightning, if it strikes a building, it can cause a surge of electric current to flow through the electricity supply of that building, and any unprotected equipment can be burnt out as a result of that excess of current flowing through it, and this can in turn cause fires. So here is a photograph of a microchip that's been damaged by an electrical surge during a lightning storm. Now, tall buildings and tall structures are particularly at risk of lightning strikes during thunderstorms, and the reason for this is because the tips of these structures are closer than the surrounding landscape to the undersides of clouds which have built up that enormous static charge, which eventually will discharge as a lightning bolt. So to prevent damage, we install lightning conductors on the sides of these buildings. You can see here in this zoomed in image the lightning conductor which has been attached to the side of this building. So a lightning conductor provides an easy, harmless path for that electricity to flow directly to the ground rather than damaging the structure of the building. So this animation here, in a very basic way, shows how a lightning conductor protects a building. Here we have the conductor, which is a big cable made of metal, and this goes down into the ground. This symbol here is the symbol for earthing of an electrical wire. This simply means that the wire goes deep into the ground and can allow any current flowing through the wire to go off into the surrounding soil and rocks of the earth. So when a lightning strike happens, and we compare this to a building without a lightning conductor, what will happen is the energy carried by that lightning strike can cause damage and fires to this building because the energy is not flowing down into the ground. It is being absorbed by the materials of the building. In contrast, when the lightning strikes the building with a lightning conductor, the electrical current and the energy that it carries can flow directly into the ground and not damage the building itself. Now, in the home, lightning again can cause damage not just to buildings, but also other parts of the building. So, for example, fires caused by the damage to electrical devices, as well as the actual damage to the building that the lightning strike can cause. So during a thunderstorm, you're told to disconnect your television and any aerials or any other electrical devices, because these wires can act as conductors, which can take the energy, the electrical discharge which is hitting the building, and channel it into electrical devices, which obviously are not built to withstand those kinds of currents. So satellite TV dishes which are attached to the outsides of buildings are also earthed, and this also protects both the satellite receiver on the inside of the building, which is attached to the satellite dish via a cable, and also the other devices within the building, including the television which it's attached to. Static electricity also poses a problem when computers or printed circuit boards are manufactured or upgraded or repaired. So typically, if you're repairing a computer or if you're building one, because the devices, the printed circuit boards of the devices are very sensitive to static discharges, including the ones that can build up on the surface of your body, such as if you've just walked across a nylon carpet, you typically will wear a static wrist strap or heel strap. This should say heel, H-E-E-L. Apologies for the typo there. So this is an example of such a strap, and these straps are actually connected via a wire to an earthed object, such as a radiator board or something like that. So So these protect the devices in the circuits that you're handling with your fingertips, such as, for example, RAM chips, memory chips, which are particularly susceptible to static discharges, by channeling away any static that builds up on the surface of your body and causing it to flow down to Earth rather than into these very delicate components. So this operator here, you can just about see, is wearing a static band or wrist strap as they're mending and looking at this circuit board. Now, another application of this is aircraft. When aircraft fly through the air resistance, the drag, actually causes a static charge to build up on the surface of the aeroplane. Now, the reason for this is because as the air molecules rub up against the surface of the plane, the friction causes charging by friction. The metal body of the plane is picking up electrons from the air molecules due to the collisions between those air molecules and the surface of the plane. So this results in a static charge building up on the surface of the plane, and this in turn causes a high voltage or high potential difference between the plane and the ground. So to discharge this buildup of static electricity, aeroplanes have small metal spikes on the edges of their wings. So if you've ever wondered why aeroplanes have these little metal spikes on the edges of their wings, that's the reason. The spikes provide an easy route for any charge that's built up on the surface of the plane to leak away into the air as the plane flies through the air. Now, when an aeroplane is refueled, a charge buildup could cause a spark. So there are precautions taken in every aspect of the refueling procedure. So, for example, a charge could build up as the liquid fuel is being pumped through the rubber hose pipe that connects the fuel tanker to the plane. So to prevent the buildup of static charge during refueling, which could result in a spark, which may light the fuel and cause an explosion, a copper wire is connected between the tanker, the metal body of the aeroplane, and the ground. This allows any static charge building up on any part of the refueling chain to leak into the ground and not cause any kind of sparks in the fuel chamber, the fuel tanks of the aeroplane. So both the aeroplane and the tanker also have special tyres which actually are designed to conduct electricity into the ground as an extra safety measure. So you can see just how seriously aircraft engineers and also other engineers that deal with the maintenance of aircraft take this risk of static charge buildup. Now, some aircraft can actually be refueled in mid-flight. So, for example, military aircraft, such as this fighter plane here, what you're seeing here is a photograph taken from the refueling part of another aircraft, an air tanker, which carries lots of fuel. It will extend this boom, this refueling boom, down to this aircraft and actually make contact with it in mid-flight and then pump fuel through this armature here into the fuel slot here. So essentially the fighter aircraft pilot and also the pilot of the refueling tanker have to coordinate their motions so that they can insert this nozzle into this refueling port here and refuel the jet aircraft in mid-flight. So as the plane flies, again, we've already said, electrostatic charge can build up on the surface of the plane. And this depends on the level of air resistance, what the aircraft body is made up of. But if you've got two different planes, such as, again, the refueling tanker and the fighter aircraft, obviously the difference in the sizes of those planes, in the speeds at which they fly, and various other characteristics can cause different amounts of charge to build up on the bodies of those two different aeroplanes. And so this difference creates a potential difference of voltage, which could create a spark as the fuel line is being connected between the two. Now, obviously, that could be disastrous if you've got fuel going between the two and suddenly you have a spark in midair. It could potentially damage both aircraft and cause a horrible disaster. So to avoid a spark, there are many solutions. The planes are connected with a copper cable before the refueling cable is connected. The fuel line itself is not made of rubber, it's made of metal, and this allows the charge that builds up to be distributed equally over both aircraft, and also this is done by a copper cable. The empty space in the fuel tanks is actually not filled with air at all, it's filled up with carbon dioxide, so that even if there was a spark, there's no oxygen for there to be an explosion. Another common application of electrostatics is the photocopier. So let's have a look at the way the photocopier works. Now, electrostatic forces are used. What you have here are the various kind of key parts of a photocopier. Now, photocopiers are quite complicated machines, but these are essentially the parts. You have the fuser rollers, you have the corona wire, and you have a photoconducting platen, which is a plate which changes its electrical charge depending on how much light is falling on it. So what happens here is, if we imagine the original sheet of paper that we're going to make copies of being placed upside down on the platen glass of the photocopier. The platen glass is the bit at the top where you lift the lid of the photocopier, you put your paper down, and then you put the lid down, and the platen glass is the glass section that you put your piece of paper that you want to make a photocopy of. So the next step is the roller down here moves over the surface here, making the platen positively charged. So as the light passes through the piece of paper, the platen is exposed to different, the platen glass is exposed to different intensities of light, and so as a result it responds by the darker areas staying more positive. So these are the areas behind any ink or any diagrams or any letters on the original document, and so these stay positively charged after the light has been exposed through the or rather after the light has been shone through the document that's being scanned. So the platen is then exposed to a fine dusting of toner, which is the essentially the ink that the photocopier uses. Now, the negatively charged toner will stick to positively charged areas on the platen, such as the area that we outlined here. So now the piece of paper on which we're going to make a copy of the original image comes in, and then the roller rolls again over the piece of paper. The corona wire causes the piece of paper to become positively charged. So the paper basically transfers the toner onto itself, and then the rollers here take off any excess toner, and also the heat from these fusing rollers sticks the toner to the paper in a permanent fashion, and so now the paper has now created the final copy here. So this is essentially how a photocopier works, and as you can see, it's all based on the principle of electrostatics. Now, ordinary inkjet printers also make use of electrostatic principles, but in a different way. Inkjet printers are called inkjet printers because they direct a fine jet of tiny ink droplets onto a sheet of paper. Some inkjet printers use droplets as small as 1 picoliter, 1 billion drops per milliliter. You get 1 billion of such drops per milliliter. So this gives you a sense of just how small these drops are. Now, the way that it works is that each one of those ink drops is charged. It's given an electrostatic charge and then moves between a pair of charged plates. And so an electrostatic force will exist between the ink droplet as it passes through those plates and those charged plates. If you change the charge on those plates, you can change the forces, and that will move those ink droplets in various directions. So the charges on the plates are constantly being changed up to several hundred times per second, so that each ink drop in that stream of ink drops, which is passing between those plates onto the surface of the paper, is landing in a specific location, which forms the required image on the paper. So this is essentially how it works. We have a positively charged plate, a negatively charged plate. The charges on these plates are continually being varied. So as the ink droplets, which are positively and negatively charged, flow between these in the inkjet, they will be attracted or repelled between these plates to differing extents, and this causes the ink droplets to fall onto the paper at specific locations. Now, if you have different colors here, the ink drops of a particular color will be charged positive, the ink drops of another color will be charged negative to varying extents, and so you can change the charges on both plates and cause the droplets of different colors to fall onto specified locations on the paper, forming the image. Spray painting is another one of these applications of electrostatics. So special powder paints have been formulated to be used to paint metal objects such as the bicycle frames and car bodies. So as the paint droplets emerge from the spray gun, they become charged, and they all carry the same charge. And since they all carry the same charge, the droplets repel each other and spread out, forming a very fine spray. Now, the metal object that you're painting with that spray has been charged at the opposite charge, and so the droplets from the spray will attach themselves to the surface of the object to be painted, and so this means that the paint is not wasted. All of it can be attracted to the object, and you can also form a very even coating of the paint onto the surface of the object without making any streaks in the paint, such as if you were using a brush to apply the paint. So essentially what you have is, for example, the metal frame of a bicycle here, which has been negatively charged, and it is connected to a power supply which charges it negative, while the mist being sprayed by the spray can is positively charged. So if you move the spray over the various parts of the bike frame, you can actually color the bike frame very evenly by making use of this principle where the positively charged ink droplets will be attracted to and stuck to the negatively charged body of the bicycle. Another very important use of electrostatics is in the control of pollution from industrial chimneys. So power stations, for example, that burn coal can produce large amounts of smoke, which is made up of ash or dust particles. Now, these so-called smokestacks are not actually giving out smoke. What you're seeing here is not smoke, it's actually water vapor, and it's usually very clean water vapor. But the reason it's so clean is because the dust particles and smoke particles have been removed. Now, to remove them, they make use of something called an electrostatic precipitator. So this type of device uses several thin positively charged wires which have been drawn out across the center of a power station chimney. The wires are charged to about 50,000 volts. Now, the electrostatic field surrounding the wires makes the smoke particles positively charged as they pass. The positively charged smoke particles are then repelled from the wire, forcing them towards earthed metal plates where they end up collecting. Now, every few minutes there is an automatic hammer mechanism that hits those plates and shakes loose those particles of ash and dust, which then fall down into a container where they can be collected and then taken away and disposed of. So here is an animation that shows how this works. So what we have here is charged wires. This is the middle of a chimney through which we've got smoke coming from, for example, a power station. The smoke contains all kinds of pollutants and dust particles. So as those particles move upwards, the charged wires causes these particles to become positive and repelled from the charged wire. They then stick to these earth metal plates. Now, these plates are metal, which means as these positive particles come into nearby to these metal plates, they induce a negative charge on the surface of these plates, which causes these to build up. Eventually, a hammer mechanism will hit these plates, and these particles will drop down into a container unit further down where they can be taken away. And so in this way, we can remove these dust particles from the gases exiting the power station, leaving behind relatively non-toxic substances such as water vapor. So one final example of an application of electrostatics. So this is a portable defibrillator. A defibrillator is a machine that is designed to save the life of a person who is experiencing a heart attack. It's essentially a machine that builds up and uses a large charge to reset the rhythm of the heart of a person who's having a heart attack. So two paddles are highly charged by the machine, and then the machine will automatically tell people nearby to stand clear. The power of the machine is about 40,000 watts. And so it then discharges the charge that's been built up by the machine is something called a macro shock. And so you, as a person who perhaps isn't medically qualified, if one of these is around in a room, on the side of a room where a person has just had a heart attack, you don't need to call an ambulance, you don't need to wait for a doctor to appear, you can simply get the machine out and it will actually walk you through the instructions as to where to put the paddles, how to switch it on, how to charge it up, and then it will say stand clear, and then you get away from the person and it will then apply a shock across. So it will discharge in such a way that the charge flows across where the person's heart is, and this can then reset that person's cardiac rhythm and hopefully save their life. So you increasingly will see these small portable defibrillators in public places. And again, they're very useful because it means that if a person's having a heart attack, you don't have to call, well, obviously you would call an ambulance, but you don't have to wait for the ambulance to arrive before giving that person help. Typically, the first few minutes while a person is having a heart attack are the critical time when, if a person can be defibrillated like this, they're more likely to survive than if you wait the 5, 10, 15 minutes or whatever it will take for an ambulance to get there. So, before I stop the recorded segment of this video, let me go into a couple more ideas concerning electric fields now. So the word field in physics is an incredibly important one, and it's something that you're going to come across again and again and again in so many different areas of physics. We're going to be talking about, for example, the gravitational field, magnetic fields, and so on. So the word field in physics has a very specific meaning. Now, I realize that we haven't yet in this physics course talked about vector quantities and scalar quantities, but quantities are just things that we can measure in physics. Certain quantities like mass are called scalar quantities because they have only scale, they have size. They don't have a direction connected with them. So if a person says the mass of this object over here is 5 kilograms, that's enough information to know what the mass of the object is. It's a certain amount of something. But if a person says the velocity of an object is 5 meters per second, then to fully describe velocity, you also need to give the direction that that object is moving in at 5 meters per second. So certain quantities like velocity, like acceleration, like momentum are called vector quantities because they have a certain size associated with them. So we can say a person's velocity has a size or magnitude of 5 meters per second or 10 meters per second, but we also need to define what direction they're moving in. So vector quantities are quantities in physics that have both a magnitude and a direction. Scalar quantities are quantities that have a magnitude only. Now, the field in physics, the proper understanding of a field is that it is a quantity which varies in both size and direction at all points in space around the object which is causing the field. So let's illustrate that with this simulation here. So if we have a charge, a positive charge, let's say we take a positive charge object and it has a charge on it of 1 nanocoulomb. Now the prefix nano means 1 billionth, 1 times 10 to the power minus 9. So this charge has, this object has a charge of 1 billionth of a coulomb. Now, if I take another object, let's this yellow sensor here will has a positive charge of its own. So you have another positive charge. From what we've said so far, it will have a force that this object here will have a field around it which will exert forces on other charges. If we have a positive charge and we place it over here, for example, it will experience a force in this direction, a repulsive force, because this is also positive. So vector quantities like force are shown in diagrams by means of arrows, and these arrows indicate the direction that the force is acting in, and the length of the arrow indicates the size, the magnitude of that force. So force is a vector quantity. It has a certain size, it also has a certain direction. So at this position in this field around this positively charged object, this positively charged object will experience a force of this magnitude in this direction, away from the object causing the field. If I move this to a similar distance away, but down here, we can see that the size of the arrow will be the same as long as it's the same distance away. It will experience the same amount of force pushing it away from this object due to the field around this object. But the direction of this vector has changed. If I move it back here to its original position, roughly there, and now change the distance from here along this line, we'll see that the size of the force decreases as I move further and further away. If I move closer, the size of the force increases. And so at all points in space around this object, the size and the direction of the vector quantity, the force, is changing. And so this is what we mean by a field. A field is a vector quantity which changes in size and or magnitude and or direction at all points in space around the object responsible for the field. Now, if I change this charged object to a negatively charged object with 1/1000th of a Coulomb of negative charge on it, we can see that the force experienced by our positively charged object here will be towards the negatively charged object. And again, at all points in space around the charged object causing the field, the direction of the force vector or the magnitude or both will change. And so this is what we mean by a field. Typically fields are understood in terms of the force exerted by that field on other objects, and the direction and the size of that force will change depending on the distance of the object we're looking at from the origin of that field. Now, electric fields are fields which affect electrically charged objects. Electric fields are fields which will attract or repel charged objects, and electric fields are caused by charged objects. So a negatively charged object will have a field around it which attracts positively charged objects and repels negatively charged ones. A positive field or positively charged object will have field around it which an electrostatic field around it which will repel positively charged objects and attract negatively charged ones. So if we visualize this field now in terms of the directions that the field will exert forces on positively charged objects, we can see these arrows indicate the directions that a positively charged object will experience a force in at all of these positions. So if I move it over to this position, that's the direction that the object will experience forces in. The further we go away from the object causing the field, the smaller the force becomes. The closer we get to the object, the greater the force becomes, and so on. If we replace this by a negatively charged object, it has the opposite direction of field lines, of arrows pointing towards it this time, because by convention, by agreement, when we draw diagrams of electric fields around a particular charged object, the direction of the arrows in that diagram, as we'll see, indicate the direction of force on a positively charged object. So we can draw the field around a particular object with a particular charge in a certain manner, which is a kind of standard manner, and you may be expected to either draw these fields or to interpret these types of diagrams. So let's start with a positively charged object. So let's go back to our positively charged object here first. Oh, I've got two objects here. Let me get rid of that one. Okay, so the way that we draw this would be to show our positively charged object, which is the reason for the field's existence, and we draw field lines. Now, field lines should start on the surface of the object causing the field, and you should draw at least 4. Now, by convention, the lines indicate the direction of force applied by the field on some other object which has a positive charge. So if I have a positively charged object, which is the reason for this field, now ideally you would draw these diagrams with a ruler. Don't draw it freehand like I'm drawing it here. And as you can tell, my drawing skills on a graphics tablet have a lot to be desired, so please do use rulers for these field lines. But because the direction of force indicated would be away from this positive charge, we always indicate the arrows on the field lines around a positively charged object pointing away from the object causing the field. So this is how you would draw the field around a positively charged object. Now, as you can see, the field lines closer to this object get closer together, and the field lines further away from the object get further apart. So this is a way of showing that the force experienced by some other object here, some other charged object here, is going to be greater nearer the source of this field than further away. So if we draw the field around a negatively charged object, it would have the same general kind of directions for these field lines. Again, my apologies for my less than vertical lines here, my less than straight lines at least. So you draw these, again, always draw at least 4 of these lines. And in this case, again, by convention, the arrows should indicate the direction that a positively charged object would experience a force in if it was placed somewhere in this field. So if it was placed at this location, it would be attracted to this negatively charged object. So we would draw the field lines for an electric field around a negatively charged object like this. Now, the reason why objects will experience forces, either repulsive or attractive, is because of the interactions between their electric fields. So if you have a positively charged object and a negatively charged object, what will happen is the lines of force, or flux lines as these are called, will interact with each other, causing an attractive force between these. The way you would draw this is like this. And you would draw the other field lines coming from this like that. So you would draw the arrows, again, according to that same convention, away from the positive charge towards the negative charge. So this would create an attractive force between the positively charged object and the negatively charged object. If you have like charges, so whether they're both positive or both negative, you would get a similar field diagram. This time, the field lines would do something like this. Rather than connecting with each other, they would kind of push against each other like this. So you have this for 2 positive charges. Like this. And if you had 2 negative charges, the field lines would be drawn in the same manner. The only difference would be that the arrows would be towards the negatively charged object. So you would draw them something like this. Again, the field lines would not meet, they would push against each other. And it's that pushing of the field lines against each other, that kind of interaction where they don't join, but they push against each other. It's that interaction between the electric fields of these 2 like charges which causes a repulsive force. So in this case, you have, let me just switch colors here. So in the case of these examples here, you have a repulsive force as a result of the field interaction. Forces, equal and opposite forces, which push these apart. In the case of this type of interaction between unlike charges, you would have attractive forces pulling these 2 together. So this is how we draw electric fields around charged objects, and it's the interactions between the electric fields which result in the forces, the attractive or repulsive forces between electrically charged objects. Now, one final point about fields, and then I'll stop the recorded segment of this lesson and go into the discussion with the students in attendance. We need to get from what we've talked about so far to the concept of potential difference. I've mentioned potential difference in a couple of occasions here. When we're talking about electrical circuits, we're talking about the reason, the flow of charge, the movement of charges. Now, generally, when things move, they have a reason to do so, and it's usually a reason connected with energy. So let's take a look at how that works in an electric field here. Let me switch off the electric field. So if we have this positive charge, we know that we have an electric field around this positive charge. And the electric field is, again, a vector quantity, a quantity which describes the direction and the magnitude, the strength of a force experienced by another charged object at all points in space around the object causing the field. Now, we can measure the potential in volts at every point in this field. Now, the potential is a way of describing the work done, the amount of energy transferred per unit of charge, per coulomb of charge that's been moved from an infinitely distant point to this point here. Now, the reason why it's described in that manner is because work done is energy transferred. If you have an object at infinity over here somewhere, it will experience no force. But at all distances which have a finite, at all finite distances, there will be some force experienced by a charged object. Obviously, the further away you go, the smaller that force becomes, but eventually, if you could reach an infinite distance, that force would be zero, and therefore that object would experience no acceleration away from this object. So let's imagine this is at infinity. It's experiencing no force, it's just floating there. This object is just floating over here. Let's imagine that this object here, which is causing this field, is fixed in place. Now, if I wanted to move this object to this location, I would have to push it against the force, which is steadily building up, which is pushing against me, moving to here. So I would have to do work. I would have to expend energy to move it to this point. And the energy expended, the energy that I have used per unit of charge on this object to move it from an infinitely distant point where it's not experiencing any force and it's just sitting there, moving it towards here. As I move it towards it, it starts to experience a force and I have to do work against that force. The energy per unit of charge on here in moving it to this point is called the potential at this point. Now, two different points, therefore, will have different potentials in this field. And the potential difference is the difference in the energy required to move an object with this charge to this point versus the energy required to move an object with that charge to this point. So, potential in volts is a measure of the work done, the amount of energy transferred in moving a charge from one specified position in an electric field to another specified position in an electric field. Which means that if we look at a distance at a particular radius from the source of this electric field, so this green line represents a line of equipotential. And in fact, because we're looking at this in 2 dimensions, but actually this is a 3-dimensional situation, in 3 dimensions this would be a spherical surface with its center centered on the source of the field. Now, at all points along this surface, the potential at those points is the same. If I move to a radius further away from the center of the field and measure the potential again, this would be another equipotential surface, which means the potential difference between here and here is always going to be the same at all points around these 2 surfaces. So potential difference, the way you can think about it, and we'll talk about this later in another lesson, but I want to define it here because we need to start building up our mathematical understanding here. So let's finish off here by talking about what we mean by voltage or potential difference. So volts is a way of measuring the work done. Now, when we say work done in physics, it means the amount of energy that's been transferred in doing something. Whenever we do something in physics, whenever we effect changes in physical systems in the world around us, we are doing work. We're transferring energy from one energy store to another. And there'll be more on this in a later topic on energy. But when we're talking about charges in electric fields, the voltage at a particular point in an electric field is the work done in moving that a charged object to that position from a point where the potential is 0, from an infinitely distant point. So the voltage as a potential difference is the work done per unit of charge. So voltage here is described as potential difference. So you can think of voltage as being an analogous concept to if I wanted to move, or rather if a ball rolls down a hill, work has been done by gravity in moving it from at the top of the hill where it has high potential energy to the bottom of the hill where it has lower potential energy. And again, this is an example of fields at work. At a greater distance from the Earth, objects have a higher potential energy relative to the surface of the Earth than on the surface of the Earth. And so, if allowed to do so, the object will roll downhill to the Earth. And it's the force of gravity that's doing work in moving it down from that higher potential to that lower potential. In a similar way, charges will move. Work can be done to move charges from a particular point in a field to another point in a field. So we can define 1 volt is 1 joule of work, 1 joule of energy transferred per coulomb of charge as that charge moves from one point to another. And the concept of voltage is going to become very important in later lessons. So we've defined voltage here. We will recap that. We've defined current, which again we'll get into in electrical circuits, which will be the next lesson in this topic. But it all comes down to this fundamental property of matter, charge. And charge causes a field around it, which can attract or repel other charges, like other quantities. Mass, for example. Mass can cause, will cause a gravitational field around it, which will attract other masses. So the concept of the field is something that you're going to be seeing a lot more of throughout this GCSE physics course. But for now, I'm going to stop the recorded portion of this video and go into the Q&A section with the students that I have in attendance with me. You've asked a lot of questions in the Q&A box, so I'm going to get on and answer those now. So if you're watching this as a recording, that will do it for this lesson, and I will see you in the next one. Take care.